Hi, and this is an update on the current state of Hopper, my programming language. That's a modern curly brace and semicolon language, but designed for small platforms. Specifically, we're looking at it on the 6502 right now. I've made a lot of changes since I last recorded some videos. Specifically, the idea of writing other languages in Hopper and hosting them on the 6502. In other words, writing a compiler or an interpreter. And in this case, we're looking at a basic interpreter. Let's run it. So right now it's uploading the basic interpreter, GIBL. Is the name of the language, Gordon's Tiny Basic, which is based on something called Nibble. And what you're looking at right now is a console across a serial port on the 6502. And we'll load up a program in there to run. I'll copy it onto the clipboard and then paste it into my console. There it goes. And this is the program we looked at last time. I'll run it again. Those little dots are tokenizing. And then it's going to draw this Mandelbrot, and it's a hell of a lot faster than it was the previous time. So what I've done is I've re-implemented BASIC as my example language, and specifically Gordon's flavor, so that I could just cut and paste the samples, and so we could compare apples to apples in terms of size and speed. But the difference this time is instead of BASIC running on its own intermediate language tokens on top of Hopper, I made a significant improvement to Hopper to be able to create inline code in Hopper's own virtual opcodes. So this BASIC is being translated into Hopper opcodes and then executed like inline code in Hopper. At the end of the day, it's still BASIC being interpreted on the 6502. But it is a lot faster than it was before. My usual benchmark is the Byte magazine Civ benchmark, and I have a version of it here written in GIBL. Now, GIBL has these peek and poke operators, and I added one to do bits because it does bytes and words, so that when you do an array of 8K, it doesn't take up 8K, it only takes up 1K because it's 1 bit per element, because it's a boolean array. Anyway, let's run this one. So the Hopper version of this takes about 8 seconds to run, and I'm on a clock of 5 megahertz roughly, 4.9. So multiply by 5 and you'll get my time historically on like a 1 megahertz machine. So about 40 seconds if you multiply 8.6 by 5. And we can switch to go and have a look at what's been driving this benchmark, which is the basic benchmark that was in the Byte magazine back in 1983. They did one in 1980 and then they redid it in 83. So let's go see what the results were back then, because they'd be the same on the same hardware. Here we go. So we're looking at running on the Apple here, and this is at 1 megahertz. And I took roughly 8 seconds times 5, so I'd take 40 seconds but times 10, because they run 10 iterations. So it'll be 400 seconds. For comparison, that would be faster than Apple Integer Basic or AppleSoft Basic. Bill Gates' one, Woz's one. It's faster than Pascal, than UCSD Pascal would have been back then. So it's pretty fast compared to the old basics, like 5 times faster than they are. Anyway, and that's this basic, which is running on top of another virtual machine. So 8.6 for the Civ. 43 for this one. There's one other benchmark that I got wind of also from Gordon Henderson's stuff. He included this benchmark. I forgot to switch back my screen. Let's do that. He included a benchmark which is Noel's RetroLab basic benchmark. None of these benchmarks are particularly good as benchmarks, but what they are is consistent across all the platforms. So there's so much historical data on these benchmarks that it makes them worthwhile. So 1.3 seconds for Noel's Retro Lab one. But this benchmark's really unfair because I'm doing 16-bit integers, so my final total here would not be the same as if you were doing floats or 32-bit integers in your language. It depends what your language is capable of. So, but that would be the same on any other version of BASIC that's only doing 8-bit integers. And I'm taking 1.3 seconds on a roughly 5 megahertz CPU. So multiplied by 5 is, what, 6.5 seconds? And we can switch to go and have a look at what those times were elsewhere. Let's switch across to there. So these are Noel's published speeds. So what did we say, 6.5 seconds? So 6.5 seconds would be really, really fast. You know, you'd have to have a 28 megahertz machine to get down to 12 seconds. So we're right at the fast end of the scale for performance. But it's not all unicorns and rainbows because I only have 14K of memory free out of 64. So I'm using about 20K of ROM for, it's a 32K ROM, 32K RAM machine, and I'm using, I keep forgetting to switch the screen back. So there we go, 14K left. And so this machine has 32 of ROM, 32 of RAM, and I have 14, about half of that RAM is left for user working space, which is not ideal, but that's the cost. As opposed to Gordon's Tiny Basic, which is only occupying less than 4K of the entire machine. I'm occupying, you know, almost 2/3 of the machine right now. Anyway, let's exit out of here and have a look at the tool again. So this is my development environment. The biggest change, like I said, was doing the inline code so that I can actually, so if we go and have a look at Hopper code, I think it's around about there. So we're inlining, here we're inlining instructions. So those are the Hopper virtual machine instructions. And we can call back methods. So this error message, if there was a divide by zero error, we can use so we can write our runtime routines in Hopper rather than in assembler, or, you know, this assembler. But that's what the Hopper instructions look like that run on the virtual machine. Lots of other improvements. One of the reasons I like these kinds of projects is because they drive overall improvements. And I'd like to consider writing, supporting other languages in this way. Not necessarily running them on, this interpreter runs on the 6502, but I can totally see writing a compiler for another language, like a C compiler, but having the C compiler in my development environment here so that I can use my debugger. I've now got a profiler. So since my last recording, I've added a performance profiler. My performance profiler, where are we? I think it's, let's go to Chrome. My performance profiler measures time in milliseconds, and it's line by line. So I can see where the hotspots are based on number of hits on the line and average milliseconds per hit. So because I'm profiling from a very, very fast computer compared to the 6502, the profiling information is amazing. I was very surprised how good it is. So I have a profiler. I also have, if I run basic here in my debugger, so I've got a source level debugger here. So if I go 10 for I equals 1 to 10, 20 print I, and 30 next I, and then I run that. And now I'm going to control C, and I'm back in the debugger. And in the debugger, I'm going to say, dump my memory. And if I now switch screens again, This is not my core competence, this lot. Okay, let's switch screens to Notepad and yes, reload this. So what we're looking at here is a symbolic dump of the current state of the memory in the 6502. So on this column on the left is the stack. So down at the bottom of the stack we have this, and up at the top of the stack other things. It's breaking out things like dictionary types. So it's quite detailed to tell me how my memory's been used and if I've got any leaks. So this tool I didn't have either last time. So I've added a profiler and I've added a really useful memory dump feature to use. And like I said, I added the inline code. Another improvement I made is to get Hopper up and running quickly on alternate machines. A lot of the runtime library is written in Hopper. So a good example of that would be the strings library. So if you don't need to port the whole string library if it's written in Hopper code. You just need to port a couple of basic APIs, and then you can write things like string split or what's this here? Another split, left padding. You can write all these APIs, last index of, in Hopper, and this will all just run on whatever platform you like. But performance-wise, it's obviously not ideal, especially if you're writing something like a basic interpreter, which is doing a lot of string manipulation. So that's another change I made since my last recording, was to make these all into what we call system APIs. So they're all written in assembler now. So I took the hotspots that I found in the profiler and wrote an assembler version of the string library, which is a whole lot faster. So that's another thing I did. I optimized the switch statement, which was also long overdue, from being a whole chain of if statements to being something that works with a table and is super fast and super convenient now. Yeah, I think that's about it. I mean, there are lots of other little improvements as well. And like I said, that's what I enjoy about this kind of approach, is it forces me to focus on the weaknesses of the system. Well, I cut that off there because I forgot about one quite major improvement that I made. Is I actually added a fifth step to the toolchain. Toolchain is like preprocess, compile, code generation, and then disassembly. I added a full optimizer. So up till this point, Hopper has only had a peephole optimizer that happens while code generation is happening, but now it's got a whole program optimizer. So it does a lot of obvious things you'd want to do, like dead code removal, unreachable code. It does inlining of smaller methods. So that's one of the reasons this got a lot faster as well. But it's not just about speed, it's about size as well, trying to get the code to be smaller. Anyway, I'll be adding these to other playlists. So there's a Hopper internals playlist, which is like the nuts and bolts of how the whole thing works. There's a language playlist, which is I'm trying to keep platform neutral, so that as I support more platforms in future, the language playlist will still apply. And then, yeah, I'm going to talk about benchmarks, and I'm going to do a walkthrough of GIBL, this basic. Anyway, thanks for watching my fascination with yet another curly brace and semicolon language.